All right, hi everybody, my name is Michael Cook. I'm a developer on the Silverlight performance team. I've been focusing on performance for about 4 years now between WPF and Silverlight. And today I'm going to be giving you some tips and tricks. In my day job, I do a little bit of framework analysis, looking at the platform from the inside to see what sort of optimizations that we can make to make things run smoother for the people that are using Silverlight. But I also take a look at client applications to see what people are doing, how they're using the platform, to see how we can better serve them. I try and take a look at the two combined to see where there are missing gaps, see where we can introduce new features to make new things basically possible to accomplish in Silverlight. And so hopefully some of the tips and tricks I give you today you'll find useful in your app building. So first, I'm going to talk a little bit about performance from an ideological level. And I think this is really important because performance, you'll see. We'll go over Visual Studio sampled profiling, some of the performance features built into the framework itself that you can use to diagnose performance issues. And I'll also go into analyzing memory usage, both managed and native, and then end on a couple of general tips and tricks. So as far as the ideology is concerned, performance is more than just profiling. I think it's really important that you make performance a part of your culture in your group. You need to have testing throughout the product cycle to make sure that you know all the way along that you're going to arrive at the place that you want to be. If you build this grand project and get to the end and find out that it's not performing the way that you want it to, it's not always going to be a 2-line change or like spend 3 days here and everything's great. Performance really needs to be thought out from the beginning, and one of the ways that you can help yourself do that is to automate your test suite. Performance is a really, really complex topic, and doing performance analysis is time-consuming. A lot of the time, you're collecting massive traces that take a long time to process, and just actually going through and rerunning the test to make sure that you're getting the right scenarios covered can be really, really difficult. So having automated performance tests can save you a lot of time. This is a way that you can track against your goals. And lastly, use your customer's target hardware. We see often that people are developing on like a 16-core Xeon machine, and then they take and try and run it on a netbook, and they're wondering why the performance isn't the same. But why would you expect that? So to sort of generalize this whole thing, I like to think of performance as a feature. It's not just something that you tag on at the end. You really need to think about it throughout the process. When you're building your specs or designing your new features, developing your architecture, it's a good time to take performance into account. Before any of the code's actually written, you want to think through your design, think about places where you might have problems, and address those in the spec phase. Once they're spec'd, you actually need to write them into the schedule. As competitive as the landscape is today, just having something in the spec, people aren't going to do, they're not going to do extra. They're going to do enough to get their work done so that they can move on to the next thing. So make sure that you're putting time in the schedule for this so that you get to it. And lastly, make sure that it's part of your sign-off criteria. You can put it in the spec, you can put it in the schedule, but unless somebody's actually responsible for it at the end of the release, nobody's going to do it. So it's really important to make sure that sign-off is a part of that. So the first thing I'm going to talk about today is sampled profiling. This is basically a way to identify execution bottlenecks in your program. So if things are using a lot of CPU, or if the animations are a little bit sluggish, CPU sampling is a great way to do that. I'm going to be covering Visual Studio 2010. And basically the way that sampled profiling works is it steps in every so often and asks the application what it's doing. It takes a sample. At the end of your scenario run, it collects all those samples, computes some statistics, and then gives some charts and graphs or some summary tables to the developer, to the analyst, so that they can make decisions about how to change their code. Sampled profiling is really nice because it's low overhead. You can take a really intensive scenario, run it with sampled profiling, and you won't see a lot of slowdown introduced just by the profiling. This is different than instrumented profiling, which actually changes the binary and actually really greatly affects runtime. I won't be covering that today. We'll just be talking about sampled profiling. This is available in Visual Studio 2010 Premium and Professional. And if you don't have Visual Studio, you can use the Windows Performance Toolkit. It's actually a free download on MSDN. So without further ado, let's jump into a demo. So performance demos can be a little bit bland, so I thought I'd hopefully try and spice things up a little bit. I've been watching this Netflix special from the History Channel on the solar system. It's called The Universe. And they start with Mercury and Venus, and they work out through the solar system, up to the galaxy, up to the universe, and they talk about black holes and supernovas. But most terrifyingly, they talk about asteroids. So I'm wondering, like, how many people are afraid of asteroids in the room? I know I am. It turns out they probably killed the dinosaurs. That vacation home in Florida that you love to go to, the Gulf of Mexico, probably one big crater. And if anybody's on like an interstate road trip right now, Meteor Crater down in New Mexico, you can go up and stand on a 1 mile wide crater and look down into the after effects of what really happens. So my demo is going to cover asteroids. I found out today that I'm the third demo that has a mock-up of the solar system. But mine goes a little bit further. This is actually a 100% accurate real-time model of the solar system. You can see the sun and the planets orbiting around with the asteroid belt. And today I'm not Mike, the Silverlight performance expert. I am an astrophysicist working at the Near-Earth Collision Monitoring Center, trying to make sure that we don't get hit by any asteroids. So I'm going to log into my super secure terminal here. And once we log in, I've been getting some complaints about the application that it's running a little bit sluggishly on slower computers, and most importantly, that the CPU usage is just kind of going through the roof. So you can see the application is not doing anything right now, but for some reason, we're seeing 27% CPU usage just sitting idly. So I want to show you how to use the tools today so that we can actually drill in and figure out why is the CPU usage slammed like that. So like I said, I'm going to be demoing the built-in profiler in Visual Studio. You go up to the Analyze menu and just click Launch Performance Wizard. And this will bring up the performance wizard that you may be familiar with. Choose CPU sampling and just follow through the wizard. This is actually new in Visual Studio 2010 SP1. We didn't used to have first-class support for Silverlight in Visual Studio in the profiler, but this is actually new in SP1. You can actually just select your zap. This is an out-of-browser app that I'll be looking at today. And just make sure that this is checked to launch profiling after the wizard finishes. And this should launch the application. Again, I'm going to log in with my super secure terminal. And basically just let the application run a little bit through the scenario that you're looking at. We're interested in why this particular screen is showing such high CPU usage, so we're just letting it run under the profiler. If you click back to VS, you can see currently profiling. And when you're ready, you can just close the application or click stop. So it takes a minute to load the symbols. And once it's finished, you can click on the profiler report. So what you're seeing here, this is actually the CPU usage over time. You can see we ran for about 26 seconds, and the application started up, and there was a spike, and then we had that prolonged CPU usage. By default, Visual Studio gives you a sort of best guess rundown. You look down this hot path to the little flame, and you can see the particular part of the code that it thinks is causing the problem. And if we click through to that, right now we're in native code and then out to manage, and it says composition target.onRendering. So this is the rendering callback that you can register for. And if you click through to this, you actually get slightly more interesting. You're drilling through the call stack when you click on the right-hand side bubble. And you can see that we're in main page, update asteroid positions. So this is pretty telling. This is actually from my code, and we're actually spending time updating the asteroid positions when, if you recall, there was nothing updating on the screen at the time that the CPU usage was high. So once you click through to that method, at the bottom of the screen, you'll actually see a little highlighted summary of where the actual time is going. So this is 11.3% of the samples going into canvas.setLeft. But again, the more telling problem was that this update asteroids method was getting called even though nothing was updating. if you click on the file, you can actually go through to the source code, and at the top of the method, you can see I'm actually unhooking the rendering event, so that's curious. But this is only happening if the control panel is loaded, so we must not have set that the control panel was loaded. So I'm going to go through to the main view model, and after the web service logs in, I'm going to mention that the control panel is loaded, and then I'm going to rerun the application. Again, we'll log in, and we should see that the CPU usage has been reduced. So there you go. So now we're down to 7%. It's still not perfect, but we'll touch back on that a little bit later. So you can see how we started with high CPU usage. We had no idea what was going wrong. We attached the profiler, and in a few minutes, we could see that it pointed us right to the exact line of code that was causing time to be spent on the CPU. So the CPU profiler is super, super valuable for finding these bottlenecks in your code. You can imagine running some complex business logic, doing validation. The profiler is going to point you right to anything that's heavy into the CPU. So back to the slides. I'm not sure why that reset. Oh. So sorry about that. So sometimes the profile isn't good enough. It's not always the case that you're going to immediately just be able to profile and see your code on the stack and say, oh, aha, I need to go change this. So this is actually an example of a profile taken after I fixed that last bug. And as you can see, all the samples are drilling down into Silverlight native code. And just try and infer from these call stacks what's going on in the application that's causing the slowdown. If you can do that, give me a call, and we'll find a place for you on the Silverlight team. But really, all you can see here is that something's going on. Somebody's rendering something. This is going to be really hard to find with a sampled profiler. Anticipating this, we added a feature directly in the Silverlight runtime called Enable Redraw Regions. And what this is you can basically get the Silverlight host, and in the settings set Enable Redraw Regions equals true. And every time that the screen's updated, we're going to tint the region of the screen that's been updated a different color. And as you'll see in a second, this gives you the ability to see what's changing on screen, even if it's not necessarily at the top of the UI, even if it's not visible. So I've already prepared the key. All I need to go do is uncomment this. And this is going to flash a lot, so if that's going to bother you, don't stare at the screen. You can see now every time that a region of the screen is updated, Silverlight actually tints it a different color. So you can see all the asteroids are being updated and the planets are rotating around. But if we go through to the login, now that pane's going to come up in front, and you can see the asteroids aren't rotating anymore, but the planets still are. And I tend to remember that I was updating the asteroids with the composition target.rendering callback, but I'm animating the planets with an attached behavior that just sets a translate transform. So I do remember writing the code to go in and actually stop this, but it must not be hooked up. So here with the rendering targets, or the composition target rendering events unregistered, I'm actually just going to go say stop planet orbits. And now we should be able to rerun this. I still have the enable redraw regions set. And now once this loads up, we shouldn't see any more updates going on. And now if we look at the CPU, we should also see that that's quieted down quite a bit. So now our CPU is down at 0. So this is a really good example of an issue where you weren't able to actually figure this out with the profiler, but using some of the built-in features in the platform, you can still get an idea of where to start. You'll still need knowledge of the code base, but just knowing what's updating on screen is a huge leg up if nothing is completely obvious. So next I'm going to go over analyzing memory usage. So memory usage is kind of a tough nut to crack. A lot of times, all people know about their memory usage is that they've built their very complex Silverlight application, and they open up Task Manager, and they see that it's using way too much memory. And users are sending in complaints, but they don't really know what that means. They don't know how to fix it. So what is memory profiling? It's basically just figuring out what's in that working set. The terminology is really confusing around memory in general. So it's a good idea to make sure that you're getting your terminology from a consistent source. I've found that the VM map documentation from Mark Rusanovich is actually pretty top-notch. So that's what I usually reference whenever I'm talking about memory. Working set itself is just the amount of committed virtual memory that's in physical memory from the process. Most developers only look at private. The distinction between private and shared is that private memory is memory that only you own. Shared memory is something that you're sharing amongst other processes. So if you're loading like a common DLL, like say there are 3 Silverlight applications running, everybody's going to be sharing the memory to load agcore.dll. But anytime that you're calling new or you're loading an image from the internet, that's all going to go into your private working set. So most people only care about private. Just getting started is actually the toughest part about memory profiling. And again, VM map is just a really wonderful tool for this. VM map, basically, once your application's running, you attach to it with this tool, and it will give you a summary of all your memory usage by category and tell you, where exactly things are going. This doesn't give you the specific allocations. It doesn't give you the call stacks or the objects that are alive. This just tells you the classification of the memory, the category under which it's going to go. I use VM map to get, I say, the 30,000-foot view of my memory usage. And then from there, I decide, am I going to go look at managed memory or native memory? And from there, I'll segue into a better tool, a more specific tool that can give me more, more actionable data so that I can make changes to the app. For managed memory, basically the first thing that I usually go to is the WinDebug and Son of Strike extension. This is a free debugger from Microsoft, and SOS is the extension that allows you to inspect the managed memory in your app. Some of the commands are listed below, but I'm going to go through like a hands-on demo at the end of these slides. And analyzing native memory is also important. Some people ask me, why do I need to know about native memory when I'm coding in Silverlight? I'm just calling new, and the garbage collector's taking care of it, and this is silly. Why am I looking at this? Well, Silverlight is actually a native runtime, and anything that you do in managed code has an effect in native code. Anything that you do will be reflected in some way in the runtime itself. If you load a new image from the internet, all you see is like bitmap image, source equals some string. But in reality, what's going on is that string is being marshaled to native code, and our imaging stack is downloading the image from the internet. It's decoding the image into a buffer, and it's holding it in native memory. So most of the time when you're doing native heap analysis, all you're really looking at is trying to figure out if there's too much image memory. This is the #1 thing that we see people complaining about. But it's good to at least understand the tools, know what's available. That way, if you get stuck in a hard spot, you can always fall back on this. And at the end of the day, you're always going to know more about your application than we can tell you. So just having that domain expertise coupled with the knowledge of the tools is going to be really powerful. Lastly, I want to go back one slide and make one more point on managed memory, actually. For managed memory analysis, WinDebug and Son of Strike, this is free and it's good. It's a good place to start. But if you're building a really big, really complex application, there are actually third-party memory profilers that are very, very capable when compared to WinDebug and Son of Strike. So I urge you to take a look at .NET Memory Profiler is one that I've used in the past. It works with Silverlight now. I'll have links at the end of the deck too, or you can send me an email. My email would be there. So one of the other things that my users have been complaining about is that the application is using too much memory. And as I said before, the first step in determining what your memory usage is just to use VM map. So actually, let me turn off enable read-our regions. So I'm going to start up the app, and I'm going to browse to that main page, and then attach VM map to see where my memory is. So when it starts up, you're just going to get a process selection dialog. This happens to be a Silverlight out-of-browser application, so I'm looking for SL Launcher. And I'm going to sort by this private column again, because this is what most people look to first. As you can see, these things are all color-coded. It may be hard to see back there, so I'll zoom in. So the orange bit is heap. This is actually your native heap. The green part is managed heap. These are the objects that you're allocating in Silverlight in the CLR. Private data is actually virtual memory allocations. These can either happen on your behalf, or you may be p-invoking directly to call virtual alloc. Image, in this case, is actually modules that you've loaded. This isn't like images like you're like downloading from the internet. And some of the others, you can read the VMAP documentation if you'd like to know more. But in reality, you're probably really only going to have to look at heap or managed heap. So that's all I'm covering today. So you can see the biggest problem category for this application right now is actually native heap. And again, I mentioned that that was going to be most likely images, but we'll take a look just to make sure. The first thing I'm going to do is get the process ID of my application so that I can attach the profiler, 7924. And in order to drive these heap traces, normally what you need to do is use the Windows Performance Toolkit with a bunch of cryptic command lines and string these traces together and then merge them together and then open them in the tool so that you can visualize them. I've tried to, I've written a script that I hope can make this simpler for you. It's called Heap Monitor, and you can get it from the Silverlight Performance blog. There will be a link to that at the end of the slides too. But basically, you just run my script, and I believe it was 7926.24. Let me double check. Yep. And this is going to turn on all the things that you need to know about. So I'm going to start the application and connect. I'm going to have to change the process ID now. 6960. And I'm attaching the tracing right now. And it spits out some diagnostic output to help you. You can see that the Microsoft public symbol server is there so that you can get symbols for the Microsoft assemblies that are contributing to the profile. It also turns on the kernel logger and the heap session. The Windows heap itself is actually instrumented so that it emits events every time you allocate something on the native heap with a call stack. So we'll see those in a moment. So that should be enough to get my profile. I'm going to close that and hit enter to stop profiling. This will actually take just a minute to merge. So I've prepared a trace ahead of time that I'm going to open up in case this one takes a minute. Maybe. All right, bear with me a minute. It looks like the Windows. Oh, there we go. So effectively, when that script completes, it's going to print out a little message that says, tracing is finished. Here's the ETL file that resulted from your trace. And once you have that, you can open it up in Xperf. And again, this is the Windows Performance Toolkit. I'm just going to kill this so the other one goes faster. And these traces can get really, really large, like I said before. So sometimes they'll take a minute to open. I think the one that I'm opening right now is actually 490 megabyte. So, you can imagine this was like a 20-second trace. If you were taking a much longer trace, it would be much larger. You'd need more RAM on your computer. So it's good to have a beefy machine if you're doing this sort of performance analysis. This should actually only take a minute more. There we go. Another note on the Microsoft public symbol server. So if you have internal symbols for your organization, there are ways to set your symbol path so that you can pull symbols from multiple locations. The Microsoft public symbol server is just one place so that you can pull symbols for Microsoft stuff and for your own things too. And there we go. Okay. So when this starts up, you're going to have a few graphs that you're going to be presented with. The first one is heap extents. This is actually, the heap doesn't grow per allocation when you're allocating things in native memory. It actually grows incrementally by predetermined amounts. So heap extents is one thing to look at, but you're actually going to be interested in heap outstanding allocation size. It's the second graph right here. And what this is literally just a per allocation. You can see little bumps for each part of the graph. I don't know if you can tell from back there, but down here there are little bumps up and down from where the animation was running. And then when we logged in, there's this big jump, and then the animation continues running, and there's sort of a smooth portion at the end. But what you can do is you can actually select a particular portion of the graph that you're interested in. You're usually looking for an inflection in the graph where a lot of memory was allocated, or if it's not an immediate inflection, you may have a long-running memory leak where you'll see a long gradual slope that just gets higher and higher as time goes on. And you can always select the particular portion of the graph that you're interested in, and once you've done that, right-click and just say Summary Table. And you actually have to manually go up and say Load Symbols. And I've cached these all ahead of time, so it should be quick. So the next thing I'm going to talk about is these category types real quick before we dig into the trace. So you can see the process is slauncher.exe. This is the Silverlight out-of-browser application that we were running. The type column, this is actually a code for the type of the allocation in relation to the rest of the allocations in the trace. So AIFO refers to the region that we were talking about, and it means that the allocations happened inside the region and were freed outside the region. So you can think of these as things that basically leaked right out of the section that we selected. We're looking for things that we allocated between and that continued living afterward. The others you can infer the meanings of. AIFI is allocated inside, freed inside. So that means a short-lived allocation that was freed before you exited the interval. And the others should be self-explanatory. Today we're interested in AIFO because we saw that big heap, and then it stayed high. And you can see there were 31,000 allocations in that window for about 62 megabytes. But basically you just start clicking through, and you want to sort by size here on the right. And you're looking for usually the largest sections of allocations first. Usually I'll have to go through a trace. It may take me 30 or 40 minutes sometimes, going through and figuring out the parts of the trace that I understand, the things that should be there and the things that shouldn't. And again, you're going to need that area expertise about your application to figure out what should or shouldn't be there. Especially if you're doing p-invoke with Silverlight, this is probably going to be really useful because you're probably p-invoking into something that's allocating native memory somewhere. So this gives you sort of a little window to see what the effects of your p-invoke is. So I'm just going to follow along and keep drilling through. You can see we're in native code. This is AG core, so we're in the measure pass. And if you keep hitting the right arrow key, you'll just keep digging down further and further. And you can see we're in an unsecured download. And eventually we end up with the bitmap cache manager decode and add. So you see 20 allocations, if you're looking here on the right. 20 allocations for about 40 megs. So this actually highlights an issue, a lacking feature in Silverlight that never made its way from WPF down to Silverlight. In Silverlight, if you pull a very, very large image from the internet and you scale it down to display it as a thumbnail, it's actually decoded the image at full size in memory. So if it's 800 by 600 by 4 bytes, that's much larger than maybe the 30 by 30 that you're trying to display it at. There's actually a workaround that you can do using writable bitmaps that I've implemented. I'll show you real quick. And this code will be available online too. And there are actually blog posts about this specific topic. But what I've done is I've taken the bitmap image and stuffed it into an image of 32 by 32. That's my thumbnail size. And put that into a writable bitmap. Now, you'd think it'd be enough just to pass back that writable bitmap and use it as your bitmap source. But that would actually hold a reference to the original stream. So it would never get freed. You'd still have this giant buffer in memory. So what we do is we actually play a nasty little trick and copy pixel by pixel into another writable bitmap that we then pass back so that the other can be freed. This isn't necessarily the greatest thing in the world either, because now we're paying runtime cost for this resizing, for this memory trade-off. But a lot of times performance is about trade-offs. there's not always like a straightforward, easy, quick way to do it. Sometimes you have to trade a little bit of processor time for a little bit of memory or vice versa. Caching is the other side of that. You can cache things in memory so that you don't spend CPU time doing them later. But anyway, so I'm going to go to my image converter, and I'm going to use my image utility. Utilities is hard to spell. And I'm going to rerun and then open this in VMMap again. So if you remember before, we were sitting at about 100 megabytes, I think, or 105 in native code. So hopefully we've made some impact here. And we'll start up VMMap. And so you can see now, if we sort by this private column, we've gone from about 100 megs down to, actually, is this up to date? Yep. And I've got a problem. Let me go back and see. I might have made a mistake. OK, I loaded up that time. So again, I'm going to run VMMap. I'm going to attach to SL Launcher. And if we sort by private, that makes more sense. So now we can see that we went from about 100 megabytes of native memory down to about 50. And again, this is something that you never would have been able to figure out if you didn't have some sort of native memory profiler. You never would have had any idea where this memory was going. So this is knowing about xperf, use this heap monitor script. It should be a really helpful thing that can help you diagnose these sorts of issues. Again, especially if you're using pinvoke, this is something you should definitely know about. So the next problematic area that we're looking at here is managed heap. You can see we're sitting at about 91 megabytes of managed heap. It's the biggest thing in this bar chart here at the top. So that's what we're going to attack next. As I spoke about before, you can use WinDebug plus the SOS extensions to dig into this. So I'm going to go into debuggers, actually run the x86 version if you're attaching to x86 Silverlight, and run WinDebug. And once WinDebug starts up, just attach to your process. Again, this is just like a normal debugger, as if we're debugging the process. And once you're attached, the magic words are load by, SOS, core CLR. What this is telling it to do is load the SOS debugger extension next to core CLR.dll. We ship the SOS extension right next to core CLR, so every Silverlight machine will always have this. Once that's loaded, that unlocks a whole bunch of new potential in the debugger for you. So the first thing I'm going to do is say dump heap -stat. And this is from the managed memory slide that I was talking about before. And what this is going to do is it's just going to walk the entire managed heap and show you all of the managed allocations that are currently alive in your application. These are sorted in increasing order by their aggregated cost. So at the bottom, you see system.decimal arrays. We have 37 objects, and by far the biggest allocation. You're going to want to read the documentation about this to know all of the ins and outs of WinDebug plus SOS, but I'll tell you a little bit about what's going on in this trace today. So the leftmost column, these are actually called meter tags. Meter tags are just basically the object ID for the particular type of object you're looking at. So in this case, we're looking at system.decimal array, and this cryptic number at the bottom is the meter tag. The reason that this is useful is you can use it to filter the results of WinDebug. So I'm going to say dump heap again, but instead of saying -stat this time, I'm going to say -mt to filter by meter tag, and then pass in that meter tag. So now we're taking a slightly different look at the debugger output this time. So instead of showing me all of the objects that are on my managed heap, it's just showing me system.decimal arrays. And you can see them all in a list at the top. The rightmost column is actually the allocation size, so you can see that they're all identically sized allocations. The middle column is that meter tag that we specified, so these should all be the same. And then the rightmost thing is actually the managed address of the particular type. So pick any line and the next thing that you can say is gc root and pass the address. And what gc root is going to do is it's going to give you the managed garbage collector root for that particular object. It's going to tell you, so you know the object is alive, but this is going to tell you why is it alive. Which objects are referencing my object so that it can't be collected by the garbage collector. And you can get more than one stack, but you can see this is a big long stack. Basically, we're going through the content presenter into a binding, in and out of native code, back to a scroll viewer, text block, yada, 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 down to threatening asteroid view model that's referencing this system.decimal. So that's somewhat helpful. At least now you know that there's a decimal array that's being held alive by this particular view model. But sometimes that's not enough. Maybe you have a type that has a whole bunch of fields that are all identically typed, and you want to know which one is causing you trouble. So again, this leftmost column is still the address. So the next thing I'm going to do is say do for dump object, and I'm going to pass the address. And when I do this, basically what we're getting now is a field-by-field breakdown of the object, as well as all the values of its fields. And if you see up in the trace above, we're looking for object 149.01.000, and that actually corresponds to one of the fields down here, 149.01000, and that happens to be the telemetry data field of the asteroid view model. So basically what we did is we went from the highest level of the managed heap, we looked across all of the memory, and we drilled down through the heap until we got to the exact object with the exact field that was causing our managed memory problem. So now we should be able to go back into the code, make a change, and hopefully this managed memory number should go way down. So if we remember, it was the threatening asteroid view model, and it was the telemetry data field. So you can see in the constructor, we're actually loading all the telemetry data right away and just holding on to it. This is actually an example of sort of a poor practice that a lot of people fall into. You should delay load as much of your data and your memory as you possibly can to ensure that you get a good experience. So a lot of times in the constructor may not be the right place to either allocate a bunch of data or load some complicated thing from a database. A lot of time you actually want to lazily load that, hydrate it only when it's asked for. And it just so happens in this application, we're not using that telemetry data anywhere. So I'm going to move this from the constructor. We can actually remove the constructor now because there's no code there. And use the question operator. This means if the field is null, then defer to the thing that follows. So in the case that the telemetry data is null, it means it hasn't been accessed before. So at that point, we're actually going to go load the telemetry data. So let's start the application up again. And once it's all loaded up, we should be able to go to VMMap and select process. So as you can see, we went from, I don't remember exactly what the number was. It was in the many tens of megabytes, 60 megs or something, down to about 5 megabytes of managed heap. Obviously, it's not always going to be this easy. Sometimes the third-party profilers are going to give you a little bit more leverage to figure out where exactly the allocations are coming from or why exactly they're still alive. But this was at least an example of, I have a memory problem. I know it's managed memory. What do I do now? So using Windebug and SOS, it's enough to get you there. It's enough to figure out, where the allocations are coming from. So now on to some general tips and tricks. We're going to lighten it up a little bit. No more profiling. The first thing is just going to be improving startup in general. As Silverlight gets richer and richer and gets more capabilities, people are building way more complex applications. And so startup time is starting to become a problem for more and more people. It's really not as hard as it sounds. The cardinal rule is essentially just to do the absolute minimum that you can to make your main page get displayed on the screen. And I mean, it sounds simple. It's not always, but there are some general tenets that you can use to sort of get you there. The first thing is just to simplify your XAML. You know, when your page gets created, Silverlight has to go through and it has to parse all your XAML. For each XAML tag that you use, we have to create objects. We have to link them together. We have to compose the tree. We have to run layout. You know, we have to hook up bindings. There are all these things. So just as much as you can, simplify your XAML. This is a general thing that a lot of complex applications use. If you look at Outlook, you know, you'll start Outlook and it'll be a blank window, and then you'll see the message list come in, and then you'll see the message pane come in. These are the sorts of things when your application gets really complex that you have to start thinking about. Load less data and or load data asynchronously. So this kind of goes back to what we showed in the managed memory example. You don't always have to allocate all your resources in the constructor. You don't always have to load everything up front. A lot of times it's a good idea to defer as much of that as possible until it's actually needed. Reduce your Zap download size. This is actually a really great one. I'm not going into a detailed demo today because Tim here has actually already posted a wonderful video on silverlight.net. The slide deck will be available after the talk, so you can go watch it. But essentially, if you have your Silverlight application that you built and you have lots of different modules with different sorts of functionality in them, the user doesn't need everything as soon as they start up. So if you can componentize things, you can download just the Zap that has your main page, your presentation UI, and then you can delay load business logic by downloading them and then dynamically hook them up in the background. And lastly, if you've gone through these first three and you're still having startup problems, it's okay to defer to a splash screen. So this kind of goes with point number 3, where if you're going to load a whole bunch of stuff for your first screen, sometimes it's better just to show like a colored background with your company logo or a little loading animation or something, while all the rest of the things are getting pulled in. At least the user isn't staring at a blank white window or IE hung or something like that. As far as runtime performance goes, some of the same tenets from startup actually apply here as well. Just reducing the complexity of your visual tree. If your application is running and you have a visual tree with a couple, tens of thousands of elements or something, every time something changes in the tree, we're going to propagate change notifications, we're going to update bindings, we're going to update layout. Everything sort of affects everything. So just the fewer things that you can actually have in your visual tree, the quicker things are going to run as a general principle. Update only what's necessary on screen. As we showed in the demo before, we had those things animating behind the background. Nobody could actually see that, but we were actually spending system resources. It's gonna tax your CPU. It's gonna increase the amount of power consumption that your app is having, which is getting more important with more and more mobile devices. So make sure you're only updating what you really need to update. Avoid updating elements with effects applied. So what this is talking about is shader effects in Silverlight. If you put like a drop shadow on a canvas, and in that canvas you have tons of elements with text boxes and things, every time something changes inside the visual tree with the effect applied, the entire effect has to be re-rasterized and in software. So this is one thing that hits a lot of people. There's a simple workaround to this. I actually have an example in my demo, so I'll go to that real quick. The first thing I'm going to do is turn back on that redraw regions. So when my application starts up, I have that login box, and you can see I have the cursor in there. And every time the cursor blinks, that entire panel is getting updated instead of just the text block that's in it. The reason this is because there's actually a drop shadow applied around the entire thing. So it's being re-rasterized every time, just like I just said. So I'm going to jump into the XAML, and I'm going to show you how you can actually fix that problem. So this is the login prompt of the application. And as you can see, I have a grid with my border, and inside the border, there's a bunch of stuff. It's all the login goo. And if you actually take that drop shadow effect off of the element that contains everything and put it on a sibling element, like this grid, Now when I run the application, nothing within the visual tree of the border is actually changing anymore. The only thing that's changing, or the drop shadow effect is applied on a grid that's actually behind everything that's changing. So now you can see we're only re-rasterizing the part that's blinking and not the entire box. So leveraging GPU acceleration for cache composition, this is another important one. If you're animating something that can be offloaded to the GPU, you should definitely consider doing it. Say, in the example that I had those planets animating around via a storyboard, setting a translate transform. That's one candidate that I could have used for caching the particular element that's being animated and turning on GPU acceleration. What this does is it means that you're not going to pay, or you're only going to pay minimal CPU cost to be updating these animations, and most of the heavy lifting will be done by the GPU. And lastly, use background workers for long-running processes. This one's important because you don't want to block the UI if you're going to go do some complex mathematical computation. You know, if you're computing fractals or something, you don't want all of your buttons to become unresponsive for the entire time. And so that's everything. Thanks, everybody, for coming, and now I'll be taking questions. We've got one in the back. Sorry, can you use the microphone? I'm having a hard time hearing you.
A performance profiler for the phone, which was showing the frame rates as well. Is that going to be in Silverlight or WPF as well?
So I don't think we're saying anything about that particular profiler yet. There's actually a feature in Silverlight Desktop right now that'll enable you to get the frame rate counter. It's actually called Enable Frame Rate Counter. And
that with correlating that data with your performance session.
I don't believe we have anything to say about that yet.
Okay.
When you were talking about reducing the zap size and loading your zaps dynamically, my understanding is that precludes out-of-browser support for your app once you do that. Is there any workarounds for that?
I'm not familiar with whether that does work in out-of-browser. I think it should. Okay. I don't know why it wouldn't, but you can either check out Tim Hewer's video, try it out, and if it doesn't work, send me an email, and we'll see if there's some other solution that we can get for you.
Okay, thank you.
Mm-hmm. One in the front here. Oh, we have an answer to that question, I guess. Okay, so the answer was you can take Meth Preview 9, the source code's available, and they have an example of doing this, and it works.
Wondering, Windows Phone.
Sorry, I couldn't hear you.
How much of this translates to a Windows Phone?
So most of the high-level principles will apply. Not all the profiling tools, like for the Visual Studio Profiler, you're actually going to have to use that mobile profiler that they showed at the keynote today. The XPerf suite of tools won't work there either. So okay. Again, the principles apply, but the tooling doesn't necessarily.
There we go. You said about automating performance tests and profiling. Are there any tool sets or tool sets coming out for that?
So as far as automating performance tests, I don't think there's anything built into the product. Vijay.
Thank you.
Sorry, what was the solution segment? So the coded UI tests you can use for this. On the Silverlight performance team, we leverage a Windows technology that you could p-invoke to. It's the ETW, event tracing for Windows. What this enables you to do is emit really, really precise timing markers from your code so that you can measure particular intervals. And we do this so that we can measure elapsed time for certain operations.
Some of the Silverlight themes have a negative effect on performance of the app.
Sure. So the question was, I talked about application complexity, and is there a way to figure out which parts of my XAML are the most complex? There are actually tools available right now that allow you to inspect your visual tree at runtime. One of them is called Silverlight Spy, and it's not linked to in my slide here at the end, but if you go to the Silverlight Performance blog, I think we have a link to Silverlight Performance Spy. I don't know if you've used the WPF performance tools in WPF at all, but basically what it gives you is a real-time rendition of your visual tree that you can step through for each particular element. So you could go to a button, and you could see all of the elements within that button, and you can actually muck around with the properties to try things out. Last call. Any more questions? All right. Thanks, everybody, for coming.